All right, welcome back, everyone. Just in a different form. We've got 8.4 today, so we're finding the sums of infinite geometric series. So today is strictly infinite. Okay, so we've been dealing mostly with finite series before we left. So today we're going to look at a series like 2 plus 4 plus 8 plus 16 plus ... which makes it infinite when you add the ... We don't know how it goes on forever. If you take a look at just what we call the partial sums, like where you add 2 plus 4 plus 8 plus 16, that goes to a certain number. But then when you add the next term, it just keeps getting bigger and bigger and bigger. So series like 2 plus 4 plus 8 plus 16 aren't very interesting to us. But if you take a look at a series like an example 1, it's a little bit more interesting, because when you take the sum of the first however many terms you want of an infinite series, when your R value is between -1 and +1, you'll see that most of the time it'll approach a limiting value. So let's check that out in example 1. So when you consider the infinite geometric series of 1/2 plus 1/4 plus 1/8, yada, 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 you'll see that your first term, you're going to have 0.5. But then when you take your first term and you add your second term, you're going to get 0.75. And then when you add your first term, your second term, plus your third term, you'll see that you get 0.88. And you're just adding a little tiny bit more the more and more terms you add. So then by the sum up until the fourth term, you'll see that it's 1/2 plus a fourth plus an eighth plus a 16th, and that's 0.94. And even by the time you get to the sum up until the fifth term, it kind of starts to stall out, and it only adds a little tiny bit more each time you add another term. So by the sum up until the fifth term, you get 0.97, which when you look at the graph of this situation, you'll see that as your n value increases, the sum, it really approaches 1.0. So we would say that the sum, the partial sum of all of these would be 1.0. Here's another example. If you considered the infinite geometric series, find and graph the partial sums for the first 5 terms, then describe what happens as the sum up until the nth term as n increases. So we'll take a look at the sum up until the first term, and we'll see that our sum is 1.5, which I'm going to change it to decimal 0.2. And then the sum up until the second term would be your 1/5 plus 1/10, which gives you 0.3. And then the sum up until the third term is your 1/5 plus 1/10 plus your 1/20, which gives you 0.35. So we're adding a smaller amount each time. So then by the time you get to the sum until the fourth term, you get 1/5 plus 1/10 plus 1 over 20 plus your next term of 1 over 40, which is 0.375. And then as your sum up until the fifth term, you get 1 over 5 plus 1 over 10 plus 1 over 20. You guys probably get this idea. 1 over 40 plus 1 over 80. And that'll be 0.3875. So as you graph this, you'll see that as your n value, 1, 2, 3, 4, 5, you can plot like 0.1. Just find a scale that's appropriate for your sum. 0.4. You'll see that you get 1 at 0.2, 2 you're at 0.3, 3 you're slightly higher, 4 you're even slightly higher, but it's approaching this 0.4 the more times your n increases. So this is sum up till the nth term. So obviously we like to create rules in math to make finding this sum a whole lot easier, which of course we do. Here's the little derivation of it. To find the rule for the sum of an infinite geometric series, we do already have one for finite, so that was in the past lessons. If you take a look at, this is pulled from example 1, where if you have the sum up until the nth term and you use the sum of a finite geometric series, and pretty much what you do is you manipulate that n value. So you want this n value to go as big as possible to really infinity. So then you think n is really, 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 really big. And you'll notice that your first term of 1/2 and your r value is the same. And so you get 1/2, and then pretty much the 1/2 and the 1/2 in the denominator will cancel. So the sum up until the nth term will really just be that numerator right up in here, which is 1 minus 1/2 to the n, which, grab your calculator. If you take 1/2 and raise it to a really, 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 really big number, aka n, really where n is going to infinity, then this whole term, the 1/2 to the n, will approximate 0. So technically your sum would just be 1. So of course we can generalize this into the fact that in this highlighter, you've got as n increases, so as the number of terms you add increase, for any infinite geometric series with a common ratio of r, and that r has to be between -1 and 1. If it's not, we cannot find the sum because you'll just keep adding bigger and bigger numbers together, which will not actually converge to a certain number. So the value of s sub n is really just the sum up until the nth term is a sub 1 divided by 1 minus r, which I don't know about you, but I think it's actually an easier equation than the sum of a finite geometric series. So here's your little core concept. This is your take-home message right in here, that if you have the sum of an infinite geometric series, here is your rule. Now, this is distinct to infinite geometric. It's got to be multiplying to get the next term. And only if your r is between -1 and 1. If your common ratio is outside of that range, then you have no sum. So make a note of that, all right? Here's a few examples of how to find the sum. We've got a right here. So you've got I, your first term, up until the infinite term of this rule. And I know we kind of left it as on Friday that you're just learning this summation notation. And so just remember that the summation notation is really just saying the sum of that term up until that term, which in this regard is the first term up until the infinite term. So we know it's an infinite geometric series, and you can find your first term, your a sub 1, by plugging in I equals 1 into the rule. So you've got 4 times 0.2 to the 1 minus 1, which you'll see a sub 1 is just 4 times 0.2 to the 0 with it, which is just 4. Which, I mean, if you were paying attention and you saw I minus 1, you kind of know that rule already. Just sometimes they get tricky. If they drop off the I minus 1, it might not just be that coefficient before the exponent. And the only thing else you need is your R value, which we know, looking at the rule, is 0.2. So then your actual sum of your infinite geometric series, you drop it into your equation that we just learned of a sub 1 divided by 1 minus r, which is 4 divided by your 1 minus 0.2. Simplify that out, you get 4 divided by 0.8, which is 5. All right. In example B, you actually have to do a little bit more work. We know our first term, a sub 1, and we have to find our r value, which you get your common ratio by taking your second term and dividing your first term. Negative 4 divided by negative 6. Simplify that out, and you get 2 over 3. So that's your r value. We know our a value. Take that out. So then the sum is just negative 6 divided by 1 minus 2/3. And you have to be careful because you have a fraction on a fraction. And that's all last chapter. You know how to deal with that. You can go and write it side by side and then multiply by the reciprocal. Just in case you've gone brain dead, you've got negative 18. All right, and example C. We know this one's super similar to B, but you've got a fraction, so you've got a sub 1. Well, I guess your other one had a fraction too, but your r value, take your second term and divide it by your first term. 5 divided by 2. So then that's really what you would be multiplying each term by to get the next. And plug it into your sum formula, and you get 2 divided by 1 minus 5 over 2. And that's equal to negative 4/3 when you simplify that out. All right, let's move on. If you feel like you need more practice, you might want to take a look at these. They're similar to what we just did, and you can practice for yourself. And example 3, I find real interesting because I love it when we link math with physics, or when we link math with chemistry, because you're going to see where these 2 classes or 3 classes overlap. So here's a little physics problem for you. A pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance of the previous swing. What is the total distance the pendulum swings? So, on your first swing, when you let that pendulum go, you're going to see that it travels for 18 inches. Now, when it travels back, it's going to go a lesser amount, distinctly 18 times 0.8. And then on its way to the right again, it's going to get multiplied by 0.8 again. It's going to travel a lesser amount, and then so on and so forth. Now, will it keep going on forever? Technically, I would argue it'll still just have a little bit of movement. So I would argue this is a case for the sum of a infinite geometric series. So all you need to know to find the sum is your first term, your a sub 1, divided by 1 minus r. So we definitely know our first term. That's 18. That's how far it traveled the first time. And it goes 1 minus your r value. Now, what is the common ratio that keeps getting multiplied each time? Well, it's that 0.8. Plug it into your calculator and you get 18 divided by 0.2, which is 90 inches. Sorry. So the total amount that pendulum swung was 90 inches. Here is another example of the pendulum problem. A pendulum that was released to swing freely travels 100 centimeters on the first swing. On each successive swing, the pendulum swings 96% of the distance of the previous swing. What is the total distance the pendulum swings? I prefer to draw my little diagram of my pendulum swinging so I can see what's happening. So on your first swing, when your n value is 1, that would be your a sub 1. It traveled a free 100 centimeters. And then on the way back, when n is equal to 2, which is your a sub 2, you would have 100, it would travel 100 times 0.96. So almost all the way back, but not quite. And then on your third swing, you would have a sub 3, which is 100 times 0.96 to the second power. You just multiply by another 0.98. And then on your fourth, you've got a sub 4, which is 100 times 0.96 to the third power. Let me erase that. To the fourth. Oh, that's even worse. So you can find the sum that this pendulum traveled by using your first term, your 100, minus, or divided by 1 minus your r value, which is your common ratio of the 0.96. Drop that into your calculator and you end up to have traveled 2,500 centimeters. All right, another application of infinite geometric series is really just back to the basics of your elementary school of writing a fraction in simplest form. So taking a decimal and switching it to a fraction. So I see this as, I want to write it as an infinite geometric series. So I'm going to chop this up and to see what is being repeated here. And I see 2, 4, 2, 4, 2, 4. So I'll write my first term as 0.24 and then add in that repetition of 0.0024. And then if I add in the next two decimal places, I would have 0.000024. And if I kept going, I would go 0.0000, two more zeros, 24, plus all the way to infinity. And I think the task in this problem, because to find the sum, I need my first term, which I have, 0.24, but I need my R value. So how do you get your common ratio? Well, you just take your second term and divide it by your first term, which is 0.0024 divided by 0.24, which simplified out, you get 0.01. Drop that back into your sum formula and you get 1 minus 0.01. And you have 0.24 divided by 0.99. Change that, move those decimals, you get 24 over 99, which actually simplifies down to 8 over 33. And bam! Who needs a calculator? Not me. All right, here's one more just to make sure you guys are all safe and sound in the math department. You're going to take 0.777 without a calculator and you're going to write it as a fraction. So write it as what is being repeated. Well, I see 7 being repeated, so I'm going to start with 0.7 plus 0.07 plus 0.007 plus 0.0007, blah, 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 to infinity. I need my R value, my common ratio. I'm going to take my second term divided by my first term, simplify it a little bit, and I get 0.1 is my common ratio. So the sum of this infinite geometric series would just be 0.7, which is my first term, divided by 1 minus my common ratio of 0.1, and I get 0.7 divided by 0.9, which is, move that decimal, 7.9. Bam. All right, well, hopefully this isn't too much of a ghetto video for you, that you've learned something better than reading it out of the book. And of course, if you have any questions, we are both Miss Eggy and Mr. Robo. We're just at the other side of an email. Please make sure that you submit your homework. Hit that little button to turn it in when you upload it, and make sure that you check your work before you submit it. We're going to post solutions for you as always, and I really, really hope to see you guys soon. I know it's been a crazy week, and I just wish you all the best, and I can't wait to see you guys all smiling and back at school. All right.